has been working on. So let me just say quickly a few words. So Bill joined the department and my group a little over a year ago, and he has two master's degrees actually, one in computer science and one in biostatistics, and he's a U of M graduate. And so he was working with Mike Benke, and he was working on his master's degree, and sometime after that, then he took a brief detour where he went to develop software for healthcare medical records, electronic medical records, and then very fortunately for us, he decided to come back to the university, and he has been working on some of our Cytoscape based tools and some statistical methods software development, and he's going to talk today about that. Oh, and also I want to mention that in addition to being in our department, Bill is a member of our Metabolomic Score, regional Metabolomic Score Center, MRC Squared, and he is doing a very important job as part of that core as well.
Thanks, Alla. I appreciate this introduction, and welcome to everybody. So as you can see, I'll be talking about MetScape, which is a Cytoscape application for metabolomic network analysis. And I should say up front that, well, first of all, I just want to get a quick idea. How many people have used Cytoscape before? Okay, that's actually good. So more than half, probably. How many people have used MetScape at all? Okay, that's actually pretty good too. So, but for those of you who haven't, I'm going to go pretty fast, and I'm not really trying to go through everything because Netscape's a pretty big program. It went through many releases, or quite a few releases before I came here, and I hope we'll go through many more in the future, but there are a lot of features, so I can't possibly do more than just sort of hit the surface things. And if you're interested, though, please do come by, talk to me, drop me an email. I hope we'll also be willing to talk to people and go into more depth on some of these things. But for now, and of course, feel free to stop me anytime with questions while I'm going. So I'm going to try to get through a bunch of different topics here. Maybe it's a little ambitious, we'll find out. Just a quick introduction to what Cytoscape is for those who haven't seen it. And then there are two main parts of MetScape. The first part is sort of MetScape Classic, if you want to call it that, which I define as anything before I got here, but does primarily pathway-based networks. It's sort of a knowledge-based system. And then the new features, so that's available currently. The new features that we've been working on is a lot of it has to do with correlation-based networks, which is more data-driven, and that is not yet available, but if anyone's interested in getting a pre-release, we'd be happy to, maybe in exchange for a little beta testing. We're hoping to release it fairly soon. And then after that, I want to talk a little bit, if I get the chance, get the time, about the statistical method that we're developing along with some folks in the stats department. And it's basically a way of calculating the data that goes into the MetScape correlation networks. And then we also are, along with that, releasing a tool that allows people to sort of go from measurements that come out of mass spec or other machines all the way through analyzing the data, creating correlation matrices, and then visualizing the networks in MetScape. So it's sort of the whole pipeline. Okay, so Cytoscape basically is an open source platform, as you can see, with a lot of different groups involved, several universities and corporations. It's been around for probably, I don't know, 10 years at least, maybe a little longer. And they basically provide a lot of the graphics and network capabilities just for a lot of different apps or plugins to do more specific disease-related or network-related functionality. But it's basically molecular interaction networks, as they say. This is just a quote from their website, but also gene expression data. And so it's evolving. It's still being released. They just released a new version, 3.2, I guess, within the last couple week or two. But the basic idea is that it's a Java application, has a really pretty extensive API. So MetScape and other applications are written in Java for that API, and Here I just put up a couple of examples of other applications. There are hundreds of these things. MetScape and MetDisease are two of the ones that we're developing. Okay, so MetScape, basically, this is a sort of covering everything slide in a way, just a quick overview of everything that goes on with MetScape. The idea is to visualize, and this is going to be starting with pathway-based networks, visualize networks of compounds, reactions that involve those compounds, and then enzymes that catalyze those reactions and genes that encode for the enzymes. And there can be, as you can see, any combination of those, variety of different types of networks available. And the input data can be 3 different types of data: gene expression data, metabolomics data, which basically is measurements of compounds, metabolites, and then gene set enrichment analysis. A couple of utilities that do that, a couple of programs. We call those concepts. I'm not going to dwell on those very much today at all. But basically, that's the sort of the workflow. And then I just wanted to acknowledge the people who've been primarily working on this. Of course, Ala was the first author on the paper, the most recent version a couple of years ago, and quite a bit before that. Most of the ideas, probably, I don't know, maybe all the ideas of MetScape are Ala's ideas originally, and she's really the driving force behind all of this stuff. And then developers, I'm hiding out in the corner here. Terry Weymouth has just a tremendous, most of you probably know Terry, I think he's online watching today, but Terry's got just a wealth of knowledge about architecture and systems design, and he also, I think, has probably written quite a lot of code for MetScape over the years. And Tim Hull was the, I guess, the primary developer prior to when I came here for MetScape for previous versions. He's now actually working in San Diego for Cytoscape. So he's still, and he was really helpful when I got started because I had a ton of questions about the re-architecture of Cytoscape. He was very patient. And then Glenn Tarsia, I haven't actually met Glenn, but I think I got his name right anyway. But Glenn worked on a lot of the database access, Hibernate framework for accessing, for basically we store information about when we build the networks, we store a lot of that in the database, and so that everything's, it's basic client server structure. Okay, so that's basically, I'll just go through how we would use the program. I think that's a reasonable way to get an idea for what's going on. And so basically, can't quite see the menus here, but there's an apps menu, and here there you'd go from apps. Oops, sorry. From apps to MetScape, build network, and you see you have 2 choices: pathway-based or correlation-based. Those are the 2 types I've talked about. So you start with the pathway-based, then you get to a panel here. And I'll go through just really quickly what some of those features are. You can see we have a pathway-based network, and the first thing is to select input files. If you want to, you can also enter manually. I'll get that eventually. Sorry. If you want to, you can enter manually enter compounds or genes. I won't cover that today, but the primary way to get a lot of data in is through the input files. So there are, if you hit the select button, I guess okay, sorry, there it is up here. So what you see is you'll have the opportunity to import 3 different files: compounds file, a genes file, and then the third type I mentioned briefly, a concepts file. A concept is just a set of genes, predetermined set of genes. It could be pathway-based or various other things. And the file formats are all simple text-based formats. But you can see you also get a chance to specify p-values and fold changes with thresholds, so you can sort of map your columns of the input files to whatever you want to be paying attention to in those files. Same thing for genes. And then I just wanted to mention that there is a tool, LRPath, that was developed by Maureen Sartor and some of her colleagues here that allows building of concepts. So if you can also go to that website and build concepts yourself, or if you have them predefined, then you can use those. Really quick, brief. Oh, maybe I just need to plug in. That was quick.
It's a bit short.
I do have a power cord, so.
I'll get it. You keep
All
going.
right, thanks. It's in here. Anyway, if I can get that out of the way. Okay, so the compound file, basically the most important thing is the compound ID. At the moment, these are CAG IDs. We hope to support PubChem IDs in the near future, but CAG is the primary ID that we use now. And then you can have, if you want to, you can have various experimental data alongside and these columns are free form. As I said, you get a chance to map them later. But they can be time series, they can be anything you want, really. The gene input file is really even simpler. Everything's based on entree gene IDs. You can also use standard gene symbols if you want to. And then just basically significance from whatever experiment you've done, a significance and fold change of each genes. And so it says here that if you want to, you can just enter a few genes. You can also enter just a whole, thousands if you want to. It really is. It's completely up to you what you get. And I'll go on with I won't talk about the concept file for now. But once you've got your input files in, you can see that the compounds and genes that you've entered now come into the panel, and then you have a choice of which type of network you want to build. So there are 4 choices. Compound reaction enzyme gene just has everything in it. And then you can see that there are subsets of those. So it just depends on your needs, basically. And once you've, I didn't have to highlight those, I guess I already did. Once you hit the build network button, you get, everybody knows the hairball, right? So you can see here, these are big data files, over 5,000 nodes, over 7,500 edges. Doesn't do a whole lot of good other than, it's kind of impressive that Cytoscape can handle networks this big. And they did a really nice job with their graphics. You can zoom these things back and forth really easily and fluently. So it's nice to have that provided. But basically, in order to really do anything useful with the network, you probably want to go through a few more steps and eventually create a subnetwork. So I'll briefly go through how you would do that.
Can you weight the networks?
Sorry?
Can you do weighted network?
In what sense? Weighted by what?
Well, there's many different ways to do it, right? But if talking about gene-gene interactions or compound drug-gene interactions, it could be what primarily metabolizes the drug, for example, would have a higher significance than, a secondary cytochrome P450 gene that metabolizes the drug or something like that. I'm just thinking.
So essentially, I'm not sure if this answers your question, but in order, the genes, you can enter the experimental data yourself, so you can essentially weight the nodes by attaching p-values to them or significance to them.
Yeah. Bill probably is going to show a zoomed-in view of that.
Yeah, okay. we'll get to a little explanation. Yeah, we do a little bit of that graphically. No, it's fine, please. It's good to get the questions. Yeah, so let's see. I guess I'll just go on to the zoom. So this does get a little closer view of, but you can see it's still kind of a hairball. It really is still just a messy bunch of nodes. You can see the sort of reddish colored nodes are compounds. The diamonds here are reactions. The green ones are enzymes, and the blue ones are genes. And you can see some of them are bigger and smaller. And that gets a little bit to the question: if they're upregulated, they're bigger. Downregulated ones are smaller. And then these green outlines mean that they're significant according to the data that you input in the first place. But again, still, this is pretty hard to interpret visually with all this mess in the way. So if you see down below here, we have the pathways that we get pathways from the database when we get the input files, so that we know basically this is a long list, probably close to maybe 100 pathways, and you can then subset your data by different pathways. So for example, here I've selected a pathway for the urea cycle and metabolism of a bunch of amino acids, and you can see a little bit that there's some yellow here in the hairball. The yellow nodes are the selected nodes, so all those nodes are nodes that are associated with the pathway. And you can also see off to the side here in the network panel that we now have 288 nodes and 333 edges selected. So we've subset the network quite a lot at this point. And then we can hit the create subnetwork button, which will then reduce down to a second, it'll build an additional network with just those selected edges. So now we've got, again, a much closer up view of glutamine, which has been downregulated and which is significant here, various other ones that are significant as well. And if I wanted to get information about any of those compounds, I could just double click compounds or genes, any of the nodes. If I double click on glutamine, I get this information panel, which has, among other things, links to a variety of databases if you want to learn more about that particular compound, and also a nice little molecular representation of the compound. There are quite a bit of other there's more information in there as well. So that's basically the general workflow for MetScape for pathway-based networks. And as I said, I skipped a lot. There are ways to expand and collapse nodes, and you can do some animation and time series things. There are just a whole lot of other features in there, but I hope that gives a basic fundamental idea of how to get started with some of these things. And probably most of you who've used MetScape have done this already. So the problem with pathway mapping, well, it's certainly useful, and we will keep it in the program for as long as people are using it, but it's not perfect. We don't have complete knowledge. So currently a lot of, it looks like we're basically around half of the metabolites that are measured by a mass spec and other machines are mapped to pathways, and there may be other pathways that we don't even know about. There are basically a lot of these known unknown features, as they're called, which are features that will show up repeatedly and reliably on mass spec readouts, but we just don't know what they are. We have information about their molecular weights and retention times, another useful piece of information that scientists are using to try to understand what these things might be, but it still is a big partitioning problem. Basically, if you have the molecular weight, you still may have dozens or hundreds of possibilities for what a molecule might be, and maybe it's not even on standard lists. Who knows what it is? So the question is there any other way to get at the information and help narrow down that long list of candidates? And so I'll, along with probably other people in the field, came up with the idea of using correlation information and just basically making this a completely data-driven process. So we don't have to know anything about the chemical behavior, chemical nature of anything that's been measured in order to do this. We just need to have measurements coming out of a machine, and then we build correlation networks based on those measurements. So here we've switched over to correlation-based network as opposed to pathway-based network, and there are just a few other fair number of features here, but I'll go through them fairly quickly. So the first thing is, again, to select an input file, and you can see then I'm showing the drop down for the column mapping, so that's similar to what we had before in the pathway-based network, where you can, whatever columns you happen to have mapped in the file, you can select what you care about. In this case, it's basically correlation coefficient, a p-value, and a q-value. That just happens to be what's in our method, but you could have whatever you'd like in there, and it'll pick up those columns. The format, sorry, one more thing. When you input that file, you get a list of compounds that are identified, which are the ones in yellow here in this dialog, and then others that are not found in our databases. Those are in red. In pathway-based networks, we would just exclude the ones that are not in the database because we have no way of linking them to other reactions or enzymes or genes. In this case, for correlation networks, we hold on to those and just call them unknowns. So anything that's in the database we'll consider a known. Anything that's not is an unknown. And for the things that are known, you get a list of possible matches in the database, and you can select whichever ones you want. Fortunately, well, in the new version, upcoming version, once you've done this process once, it'll remember at least your most recent choices, so you don't have to go through it every time. But as you can see, when you make choices and you get a KEGG ID that goes along with it, you can click on the link if you want to make sure that's the one you want, and so on. But it gives you a chance to identify, because input files, I mean, it's one of the hardest things in the field, I think, to determine what are good names for compounds. It sounds like something that should be easy, but I think probably everybody here knows that it's just not. People call things different things. the range for the edges, basically, some of these networks are very large to start with, and correlations can be insignificant or not significant, close to zero, or they can be very strong. And so right away, it's important to have a way to filter the edges in the network and just get down to the things that are most important to you. So there's a mechanism here for both on the negative and positive ranges for correlation coefficients to adjust your ranges, and then based on that, you'll be told how many you're actually currently including in your network that you're going to build. At the moment, we're including everything because we haven't filtered it all. Quick overview of the input file that was used to get this to this point. It's just simple 5 columns. The names of the 2 metabolites, the correlation coefficient between them. This is actually the input format that we use for our method. Correlation coefficient, p-value, and q-value. As I think I mentioned, you wouldn't need these. You could do just 1 column of data, and you could basically do whatever your particular method involves. We try to be as flexible as we can, but it is at least 3 columns with pairwise comparisons of some sort between the compounds for every pair of compounds. It's also, this is the column-based form. We also allow a matrix format, but so it's just usually an Excel spreadsheet. But the reason that that's not really adequate for our purposes is that it really only gives you a chance to do 1 measurement. So you can't, if you were to do p-values and q-values as well, you'd need 3 different worksheets. It gets complicated in a hurry. So we support this format if you only have 1 measure that you care about, but we recommend the column-based format. And then back to the network, once we push the magic build button, we get one of these things. It sort of reminds me of spirograph when I was a kid. I don't know how many people remember that, but yeah. Basically we draw every possible edge. So every pair of compounds has a correlation. Some of them are just very weak. And so we initially, if there's no filtering, we draw everything. The thin lines, which is in this case just about everything, are the weaker correlations, and then the thicker edges are the stronger correlations. They actually get thicker, and they're done in several levels, so you can sort of visually pick out right away what is significant and what's not. And then the edges are 2 different colors. Obviously, the red edges are for positive correlations, and the blue edges are for negative. Oh, sorry. This is actually there's a story there. And just one other quick note: the sort of purple, light lavender, whatever colored nodes are the known compounds, and the white nodes are the unknown compounds, things that weren't found in the database. Okay, so what went wrong here? Well, nothing actually went wrong here, but as you can see, we've got 9,700 edges. So this is a slightly larger network. It's only 140 nodes, so it's not even a large number of metabolites for most purposes. It can often be as many as 1,000 or more. But in this case, 140, and if you decide you're going to draw all the edges, well, that's what you get. So clearly that's a case where you'd want to filter. And so in this case, we're actually mapping based on q-value. So that was recognized by the program as essentially a measure of significance. So the sliders changed. Instead of 2 sliders, you've got just 1 slider. The edges are now black because there's no positive or negative anymore. Right. But it basically, if you now filter, here I've got the slider set to 0.01 as the upper range. Now we get a much better, much more readable network just by subsetting. As you can see, now we have only 117 edges instead of the 9,730 that we had starting out. So much more interpretable. And I actually, well, one just quick thing, you can see there's a floating label here. These guys are pretty small sometimes, so this is just a tooltip. If you mouse over any node, you'll get the name of it. And again, we bring in, sorry, back up. We bring in pathway information. So for any of the known compounds, we also bring in pathway information, as we did with the pathway-based networks. The reason for that is you still may want to subset your data based on pathways. So even though the edges aren't corresponding to those pathways in any, well, they may, but they're not a priori corresponding to the pathways. You still may want to have that information and use it. So couple of interesting stories start showing up right away, and based on the work that we've done so far. And so I wanted to really briefly go into a couple of things that we found and that are encouraging that methods actually get finding us things. It's really a little bit blurry here, but these are, I guess, acylcarnitines, fatty acids that have different size tails, I believe. Is that my biology background is not as strong as I'd like it to be, but I believe that's the difference. But anyway, C18, 16, 14, they're getting shorter, and you can see they go all along 14, 12, 10, 8, 6. So they're corresponding, they're correlated the way you'd expect them to be right down the line. And then right at the end, well, there's this unknown all of a sudden. Well, what's that doing there? Well, we asked some colleagues what that might be, and turns out it is actually just another C6. But in the untargeted assay, they just didn't have an internal standard for it, so they did not recognize it as anything. They just had it as an unknown. So we didn't identify anything novel here, but we did help them to realize that when this shows up on their untargeted assays, that is C6, and at some point this is in our core. They're buying more and more compounds, and they're getting more and more standards built up. So eventually they'll be able to go back and say that this was C6, presumably, if they want to do that, make a notation, or whatever. So we found that's something that came up right away. Another kind of thing that happens fairly often, it's kind of a strange setup here where tyrosine shows up, and then it's got 3 unknowns with it, and they're all intercorrelated pretty strongly. Now, if you notice, just based on the names that we had in the input file, this is essentially molecular weight number, 182 point something. They're all very similar. And then RT is retention time, also, again, very similar for all 3. Turns out that those are also essentially what you get for tyrosine. So these 3 are probably, we don't know for certain, but probably just duplicates of tyrosine. So that helps the analysts filter out repeated duplicates so that they can basically, instead of just saying, well, we have 200 knowns and 1,000 unknowns, well, maybe the number of unknowns is actually quite a bit fewer than that, and this could help them identify some of those.
I don't know if you said that, but I think, may I interject
Sure.
with that? So one cool thing that Bill did here, I don't know if you guys noticed that the edges are actually weighted. So the thickness of the edge is proportional to the strength of the correlation or whatever is mapped to it, which is sort of, and I think, so you can explain how you did that, but I think that's a pretty clever,
Right, so yeah, so
pretty intuitive, at least seems to me.
yeah, so for people online, that what I was mentioning is that the thickness of the edges corresponds to the strength of the correlations, and so the thicker the edge, the stronger the correlation, and you can't really tell much of a difference between these because we've already filtered down to things where everything's significant. So it basically it assigns the thickness based on the entire data set. So once something's significant, you can't filter it into not being significant. But that gives, again, a visual representation of what's going on. So we're still working on more stories, and in fact, all of this week has gone through pretty much this data set with 140 nodes, and has, I believe, sounds like a story to tell about pretty much everything in the whole data set based on this method. So there's still confirmation, and we need other people to look at things in order to make sure that what we're finding is right. But it certainly is encouraging that we're finding things that are meaningful so far. Okay, so far everything I've mentioned is basically how to display correlation networks. They don't have to be, they're flexible data, flexible input data. There's no one method that was necessarily used to generate any of that stuff. Well, so we thought, well, let's come up with something. Maybe we can internally do something. And in fact, the data sets I've shown have all been generated with our internal method that we're still tweaking, but we have it pretty well defined at this point. And before I describe it, I just want to mention that this is work, of course, with all involved. George Michaelitis is a professor in the statistics department. His recently graduated student, Samantha Basu, has done a lot of the writing the R code and sort of, I'm sure, the nuts and bolts of the statistical part of the analysis. Chuck Brandt is in charge of the MRC squared core. Steve Brown is also the director of the core. have provided a lot of insight in terms of the biology and biochemistry, and have helped us identify some things when we're not sure anymore, when our knowledge has gone to the limits of what we can do. So the basic idea is that related metabolites, I've sort of already touched on this, but related metabolites may be correlated across different samples, different blood, plasma samples, tissue samples, whatever happens to be used in an experiment. And the relationships may not be based on known pathways or shared pathways or chemical similarities, or it's hard to say exactly what all the reasons could be, but we think that just by looking at data, correlation data, that we can probably determine meaningful relationships. So one idea would be just to use Pearson correlation coefficients. Simplest, generally used coefficient, just the easy formula here. And you can get direct versus indirect association here, but you do need more samples than you have metabolites in order for that to work. Actually, I think that's not true. I think I put that in the wrong place. Sorry. So ignore that last line on that one. It's supposed to be on this slide. If you want to go a little further than Pearson and actually get down to the relationships in a more directed way, there's what we're calling a basic partial correlation modeling approach. Partial correlations are obtained by basically taking any two metabolites, say M1 and M2, regressing each one on all the remaining metabolites in the data set, saving those residuals, and then calculating a Pearson correlation between the residuals. And that is, at least in theory and in practice so far, allows a much more direct comparison. Rather than a cluster of intercorrelated compounds, what you get is maybe a line going from one compound to a second to a third, where you know that those are pairwise relationships and they're not influenced by the sort of confounding relationships among other intercorrelated compounds. But in this case, now this time I mean it, you do need more samples than number of metabolites in order for this method, for the regression to work. So we have to get a little fancier than this. Not everybody has a whole lot of samples. So if you have fewer samples than metabolites, I won't go through the whole statistical part here, especially since I'm running short on time already. The bottom line of this is that there's a graphical lasso method. It assigns a penalty which effectively reduces the number of metabolites by, my understanding is, taking weaker correlations and forces them to zero. That's the gist of it. It's way more complicated than that, but anyway, that's the general idea. So I won't spend a lot of time on that because I don't have much time, but it is still pretty easy to implement. It's not really complicated to do. There are some issues, the most important being that estimates are generally biased, but there is a bias correction, which is called the DG lasso method, which is the debiased graphical lasso method. And that's what we're using, basically. So we basically give the user an option between the basic method in our tool and this DG lasso method, which we think is about the best approach. It also works really well when, in the case where n is greater than p, it still behaves about as well as the basic method. Still, it turns out that Pearson correlations are really useful for filtering compounds, for filtering nodes. If you think visually of a heat map is the usual way that people visualize these correlations, and Pearson correlations will often give clusters of nodes that you can pick out right away, and then if they're sort of along the diagonal. If you see a long part of the diagonal where there aren't any other intercorrelations or there aren't very strong ones, those are likely nodes that are not correlated with much of anything, and you can just filter them out. And so we've got that implemented. Basically, if you choose a threshold, correlation threshold based on Pearson correlations, you can eliminate a number of compounds, get rid of noise basically, but you will still retain metabolites with the strongest partial correlations. And there's actually a pretty good theoretical foundation for that George Michaelides has been working out. So it seems to be intuitively true, but also theoretically makes sense. So we have the last part, I wanted to sort of talk about the workflow, basically, of how we go from the data coming out of the machines all the way through to a MetScape network. And so this is a standalone Java tool that is written that allows us to go through the whole process. Basically, first put in an input file, which essentially just looks like a whole bunch of samples for a whole bunch of compounds. These are just measurements. In this case, these are log2 transformed and scaled to normalize the data. We allow those options in our tool, but those are very important things to be doing. And most people know that to clean the data, you don't just want to go with measurements that are all over the map for different compounds. They won't behave well when you start using these methods on them. So as you can see, we do allow log transform and auto scaling, not a comprehensive list of things, but if you want to do that yourself, in this case, we've already done it. Also allowing for a couple of different file formats. Samples can be either in rows or columns, and they can either be labeled or not, just to try to make it a little more convenient. But as I was mentioning, we still will want to use Pearson's correlations for filtering, potentially. We can, if we want to, just go straight to the partial correlations at this point. But if we want to do some filtering, we can do Pearson's correlations, and then in particular, if we hit the View Heat Map button, it will bring up a quick heat map, in this case, small data set, some amino acids, and you can just get a quick visual idea of what's going on here. As I was mentioning, here are a couple nodes that don't look like they have anything off diagonal going on. Those will probably come out quickly if you do any filtering. But where there are stronger blocks of correlation, leucine, isoleucine, valine, those likely are going to stick around no matter how much, they'll be the last ones to go. I should mention all of this, the user doesn't have to know anything about R, doesn't even have to know that R is running in the background. This is all done on a server that's running R. So basically the client, they don't have to have R installed on their machine. They just have to just give us a data file, and then we do everything else on the server. So I think that's pretty flexible, I hope. Now I've filtered, basically set the Pearson's correlation threshold somewhere just under 0.6, and that's not tremendously strong, but you can see we've already got down to 14 out of 23 metabolites, and then we can choose between the two methods I mentioned, either the basic or the DG lasso penalty method. And then when we finally hit the run button over here, and then the fun part here, depending on how you want to do this, if you want to, you can always just view results in any of these cases and save results. So if you just want to deal with the files, you can do that. But if you want to go through the whole step all the way to the visualization, you can do that here. So you can just say view network, and you don't have to know about Cytoscape, you don't have to know about MetScape. If you have them installed, basically it'll come up. I should say that there's some steps that have to happen here. But if you have Cytoscape and MetScape already installed, you will just get the network that will filter. We have it filtering on Q values with a threshold set already at 0.1, and there's your network. If you don't have Cytoscape installed yet, it'll prompt you if you want to install it. Then when it gets through that, it'll launch Cytoscape. If you don't have MetScape, it'll ask you if you want to install that. So it tries to find things. This is actually something that Tim Hull did at Cytoscape for some of their applications, and he was happy enough to let me borrow it, so I appreciated that. But it's nice to be able to just push a button and be prompted and basically end up with a nice network and be able to, this is a live version of MetScape now. You can just do everything that I mentioned before with the network and manipulate it any way you want to. So you basically just gone from getting a column-based set of measurements from compounds all the way through to visualizing and having pathway information and so on. So we hope that that is useful. And other than the highlights, I think that's pretty much it. So thanks a lot, and encourage any questions you have.
Are there links to references for the methods you used?
Not yet. That's a good. So the question is, are there links to the references for the methods that have been used? I'm assuming you mean the statistical methods.
Yeah.
Yeah. So they will be. We hope. We're working on a manuscript. This is all pre-publication and pre-release. So this is nothing has been. There are no.
You'll have them built into the tool itself.
That's a good question. We certainly will have information. There will be an explanation of what we're doing, and it's a good idea. We can definitely put, assuming that the trick is we want to release at the same time that we submit the manuscript. So it'll probably not have a link right away, but then as soon as it becomes official, it will. Actually, would you be interested in seeing links to related references as well, or just what we end up writing up?
I think it's a very good question, because I think the method itself is quite novel.
Yes. Yes.
This is really like, this sort of correlation-based analysis. It's a really hot topic in the sort of whole field of metabolomics, and everybody's very excited about it. But I think what Bill said is true, that, people so far have gone as far as like basic partial correlations. All this graphical lasso stuff is quite novel. So I think the idea, there's some, there's only one reference that I know of so far in some obscure, journal or proceedings or something, so there's not a whole lot to refer to. But what Bill does have in all various places throughout these two tools are like little question marks or whatever that will sort of, explain and give more information.
And now that you know that this is an important method, well, fortunately, Marcy passed out the sign-up sheet. So now sign the non-disclosure agreement on your way out, and we'll know anyone who's here and didn't sign it. Any other questions? So either I went a whole lot too fast, or
No, it's great.
Okay, great. So yes.
What kind of bias do you get from the graphical lasso?
Okay, so the question is, what kind of bias do we get from the graphical lasso? Unfortunately, I don't know the answer to that question myself. George Michaelitis, our statistics professor, would definitely be able to answer that in detail. I guess I think probably the Friedman reference it goes into detail on that. But if you want to drop off an email, I can get back to you on that. But yeah, I do have a biostatistics degree, but I have been only marginally involved in the statistics in this whole project. So unfortunately, I'm not the right person to ask.
I don't know the answer to that either, but I'm sure it's known. So I think we can probably look into it and get that information.
But it is a good question, for sure. Okay, I guess that's it.